mu arkadaşlar?
Geliyor hocam.
Geliyor mu sesim?
Geliyor hocam, evet.
Şimdi geliyor mu?
Hocam siz bizi duyuyor musunuz?
Geliyor.
Geliyor sesim.
Ali geliyor değil mi sesin? Tamam. İyi geliyor değil mi? Peki. Şimdi pure bending'den bahsediyor idik. Nereye geldik bakayım bir. Peki tam şurada kalmıştık. Önce şurayı bir tamamlayayım. Arkasından devam edeyim. Geçen bir Zoom toplantısında sesimin iyi gelmediğini söylüyorum. Onun için soruyorum. Boğuk geliyor dediler. Bir mikrofon aldım. Eğer boğuk geliyor derseniz onu takacağım çünkü. Her neyse anladığım kadarıyla fena değil. Şimdi şuradan bir devam edelim. Now, this equation 5 is the basic equation for the bending stress. Okay, we obtained this last course. Now, I am going to say a few words about that and then continue with the further problems and derivation. But first, let me add this. The equations 4 and 5, I mean this equation, and as a result the fifth one, where we replace y with c to define the maximum strain, are called elastic flexure equations. So, equations okay, will bir saniye arkadaşlar. Her seferinde bir problem çıkarıyor. Okay. Tamam. Okay, equations 4 and 5. Equations 4 and 5 are called elastic flexure formulas. Okay, so just know them with this name. Okay. Bu arada ben sizi görmüyorum. Şöyle yapsam görecek miyim acaba? Tamam, şimdi görünür hale geldi. Peki. Şimdi now and the normal stress is called, onu da yazayım. The normal stress, which we have defined by sigma x, is called the flexural stress. Okay. Now, the ratio of I over C depends. Now we discussed this in torsion. Only geometry and is called elastic section modulus. Okay. Just a minute. Bir saniye arkadaşlar. Buraya bir şey girdi. Okay. It's called elastic section modulus. Şu dersi sınıfta doğru anlatamadık. Çok canımı sıkıyor orada. Elastic section modulus. Okay. So, if we call S as I over C, then S is equal to M over sigma allowable. It means that if you know your moment, and if you have selected your material, sigma allowable, then you can determine S, which at the end depends only the geometry on the cross section. Okay, so you can easily design the member, the geometry of the member, which satisfies the requirements of the design. Clear? As we discussed this in torsion. So here, obviously, the mean stress sigma 1, without referring to any other quantity, is M over S as our sixth equation. So if you look at this equation, sigma M is inversely proportional, okay, to S, the second modulus, and beams should be designed with as large a value of S as practicable. Okay. Şimdi niye bugün az öğrenci var sınıfta? Peki.
Yarın termodinamik sınav var hocam.
Burhan Gözen, duyuyor musun beni? Burhan, duyuyor musun? Sesin gelmiyor. Burhan.
Hocam Burhan konuşuyor şu an ama duyamıyor musunuz?
Hiçbirinin sesi gelmiyor neyse. Hasan, bir şey mi söyledin?
Hocam sesi geliyor diye
Senin
söyledim.
sesin de gelmiyor. Nedense bir saniye. Hasan? Hasan, sesini duyuyor musun? Hasan Güde. Burhan, sesimi duyuyor musun? Hiçbirinin sesi gelmiyor nedense. Her neyse. Burhan, mikrofonunu aç bakayım bir. Konuş, sesim geliyor mu bana? Benim sesim geliyor, seninki bana gelmiyor. Mikrofonun çalışıyor mu? Peki. Chat'e bakayım, orada ne diyorsunuz? Benim hoparlörde bir sorun olabilir mi diyorsun? Olmaması gerekir ama neyse. Hiç değiştirmedim bir şey ama bir şey karıştı herhalde. Peki. Neyse, ben sizi duymuyorum arkadaşlar. O yüzden de soru soramayacağım maalesef. Şunu söyleyeyim. Bir şey burada bozuk mu nedir anlayamadım. Hoparlör. Peki. Burhan, bir daha bir söyle bakayım bir şey. Şimdi geliyor. Tamam. Şimdi Burhan, sana şunu sorayım. Belki hatırlıyorsun, belki hatırlamıyorsun statikten. Şu 5 nolu denkleme hepiniz dikkat edin buraya lütfen. 5 nolu denkleme bakalım. Ya da 4 nolu yani. Moment of inertia hesaplamayı hatırlıyor musun statikten? Peki. O zaman sana şunu sorayım. I want to calculate sigma x. I know mz. Okay. And I am going to design a beam. Now, this is the beam. And the moment, the force is perpendicular, so a bending moment is this, right? Mz. Clear? Okay. Now, I am using the same beam. same cross section, same material. This is the force of the external force, and this is the external moment. Now look, same material, same beam. Which configuration do you prefer? The one on the right, the one on the left? Yes, good. Look. Yes, look, since sigma is inversely proportional to the IZ, and since from statics we know that the moment of inertia of this is much more greater than that, we have to use this orientation for the design. Is this clear? Look, arkadaşlar dinleyin. Look, we didn't change anything. Same moment, but however, same material, same cross section, same cost. But if you use this configuration with this loading, you will carry very low force than you can carry with this. So therefore, in the design of the beams, we try to keep IZ as greater as possible for the same material. That's why such I-beams are used in the beams, because we try to remove the material away from the neutral axis. If you do that, for the same cost almost, you have higher moment of inertia. Please keep this in mind. Okay. So never use this configuration. You can carry a lower force because you end up with higher stresses by referring to the equation that we obtained. Okay. Thank you. Now, one other topic that I want to mention very quickly is this. That is deformations in a transverse section. Okay. Deformations in a transverse section. Now, I'm going to use a figure here. From the book. Maybe it's easier to explain the problem here. Okay. This is the fourth chapter. And let me copy this and paste to the. Okay, now look, I think the figure is clear and it's available in the book. Now, we are applying a moment to bend the beam. So this beam is bent like that, clear? And this is the radius of curvature. So when we bend this beam like that, since the upper portions are in compression, this rectangular cross-section changed now. The cross-section was a rectangle before, but when we bend it, because of compression, upper part increases in the transverse length and lower part, because of tension, decreases in the transverse length. So what you have is such a cross-section as you see here. And because of that, you end up with a different curvature, which is defined by rho prime. This is called as anticlastic curvature. Okay. We are not going to use this very frequently in our courses, but just know that. So rho is the rho that we know. However, because of this deformation, now look, the basic strain is AX, but since due to bending, we also have transverse strains from Poisson's ratio. So due to bending, okay, in addition to epsilon x, which is our measured strain due to bending, we have epsilon y, which is equal to minus nu times epsilon x. And we have epsilon z, which is equal to minus nu times epsilon x. And as a result, remember, we said that epsilon x in such a problem is minus y over rho. Remember the derivation that I have done. Since this is the strain due to bending, we know that the strain in y direction is nu y over rho, and the strain in z direction is also nu y over rho. Now, knowing these strains, we can say that rho prime is the radius of curvature of the transverse section. Okay, this is the, as you see on the figure, radius of curvature of the transverse section. Transverse section, right? And it is related, its equation is this: rho prime is equal to rho over nu, and anticlastic curvature, okay, is the following value. Okay. Anticlastic curvature is this, called anticlastic curvature. When we say curvature, remember, we are talking about the ratio 1 over rho prime, and that's equal to nu over rho. Okay. Şimdi arkadaşlar, şurayı kapayayım ki daha büyük görünmeli. Bahsettiğim şu. Gene şu kağıt mendil üzerinden örnek verildi ama. Şimdi bakın. Bu beam olsun bizim. Tamam. If I bend this beam, this is the radius of curvature, rho. And 1 over rho is the curvature. Rho is radius of curvature. 1 over rho is the radius of curvature. This is the actual bending. I mean, I bend it. This is the radius of curvature, right? Now, I'm not talking about this by anticlastic curvature. Anticlastic curvature is this. When I bend this like that, on the cross section, this portion, because of compression, increase in length. The lower portion decrease in length. So this rectangle now is not anymore rectangle. And then these two defines a new radius of curvature. This radius of curvature is rho prime, and 1 over rho prime is the anticlastic curvature, and it is given with the equation that I mentioned. 1, rho is our actual bending deformation. This anticlastic curvature is related with the cross section. Probably we are not going to use too much, but just know this definition, okay? I think it is now clear. Oldu mu arkadaşlar? Peki. Okay. Eğer bir sorunuz yoksa problem çözeceğim. Okay. Now, yeni sayfa açalım şöyle. The problem is a very simple problem now. It is the problem 141, okay? But I want to solve it to make an understanding for the problem. Home. Let me first copy the problem. Okay. Paste. Now, this is the statement of the problem. And for this simple problem, here is the figure. Paste. Now look, knowing the couple shown, X in the vertical plane, determine stress at point A and B. Very simple problem, but it gives an understanding for these problems. Now, for the first few problems, I am going to repeat this 2 or 3 times. What is this? If we are solving such a problem, first, attach a coordinate system. Is this clear? First, attach a coordinate system. For this purpose, let's use the coordinates given in the book first. I mean, let us use the same approach for that. So, first, okay, Now, I am attaching a coordinate system, this one, right? Okay, let me redraw this. It passes from both A and B like that. Say that this is y-axis, this is z-axis. As a result, I have here these axes. This is the y-axis, this is the x-axis. First, please put a coordinate system always. Then, since this is the moment that I have seen, it's obvious that on this figure, this moment is the following vector. Okay, this is the moment which I am going to indicate by mz, the same moment. So I'm saying that this is mz, referring to my coordinate system. Please be careful about these signs. Okay, now I located the moment to the side view also. I am using a new coordinate, a coordinate system which is not good in the problem because without a coordinate system it is meaningless. Then you have to follow the following steps. First, okay, find the centroid always. Find the centroid. In this problem, we know the centroid of the cross section. This is the centroid. You don't need to find in this problem, but you have to check. 2. Second, find the principal centroidal axis. Find the principal centroidal axis. Now, here, for a circle cross section, there is no problem. All sets are principal because of symmetry. Due to symmetry, all axes. Due to symmetry, all perpendicular axes. So we don't need to find. They're already principal centroidal axis. So these are the first step. And third, these will be clear later, but you have to check. Find the components. Bunları ileriye dönük olarak iyice öğrenin diye yazıyorum. Find the components of the moment, whatever that, on the principal centroidal axis. On the principal centroidal axis. So, let us look at this problem. We know the centroid. Y and Z are already principal axis, and moment is on Z with a principal centroidal axis. So therefore, we can use sigma equals to MC over I. Clear? So, for this problem, the stress is sigma. It is in the x direction, perpendicular to the surface, and the equation is minus mz times y over iz. So this equation is valid for the whole cross section. What I need is the moment of inertia iz. What is iz? Iz is equal to, remember the equation, pi over 64, okay, statics, the outer diameter to the power 4, minus the inner diameter, 30 to the power 4. Now, moment of inertia is 85,903 for the cross section. Okay. And what about M? The moment mz is given in the problem as 500 newtons meter. Okay. So it is 500,000 newtons millimeter. I know the equation. I know the moment. I know the iz. These are valid for whole cross section. Okay. So, therefore, for this cross section, my equation is this. Sigma x is equal to minus mz, 500,000 newtons millimeter. I don't know why. I mean, y may change. It's up to you. For every point, you end up with a different value. And iz is 85,903 millimeter to power 3. Now, this equation is the equation that gives you the stress at any point defined by y. Okay. Now, for point A, y is equal to, okay, who is going to tell me what is y for point A? It is equal to, yes?
20.
20, yes, it is 20 millimeters. Okay. And then sigma x at A is equal to minus 116.4 megapascals. And there is compression. Okay. On the other hand side, for point B, now y is equal to, let's turn back here, is equal to, yes, 15. So y is equal to 15 millimeters. Just put in the above equation. So the normal stress X at point B, obviously smaller than that, is equal to 83.7 megapascals. So a lower stress, which is again in compression. Okay. Now, if I ask you the stress at this point, say D, what do you say for me? Do you know its magnitude?
Hocam same as A.
Tam altta olsaydı ne olacaktı? Evet, its magnitude would be same with A, but its
But the
sign is,
sign will be different. It's tension.
its sign is positive. Okay, why? Because of this moment mz, in this region, all these points are in compression, but in this region, all the points are in tension. Okay, so the points below z-axis are in tension, the points above z-axis are in compression because of the moment. Any question?
Hocam birim milimetre küp değil de milimetre üzeri 4 olması gerekmiyor mu?
Bakayım nereyi söyledin?
AZ için.
Evet, haklısın. IZ şunu diyorsun değil mi? Evet.
Evet hocam.
Kesinlikle 4 bu. Niye 3 yazdım bilmiyorum.
Bir de aşağıda da aynısı var da milimetre küp
Aşağıda
85.903.
bakarak yazdığım için onu da yanlış yazmışım. Pardon. Tabii ki 4. Correct these. Okay. Now, any question? I'm going to solve another problem. This problem is a little bit different than the others. Okay, let me copy. Paste. And it is figure also. Now, in this problem, okay, knowing that the beam of the cross section shown is bent about the horizontal axis, and that the bending moment is 6 kilonewton meter, determine the total force acting on the top flange. Okay. Now, first, what is the total force on this cross section if there is only pure bending? Who is going to answer? Total force on this cross section for pure bending. Yes? Fikri olan var mı arkadaşlar? Pure bending'de kuvvet var mıdır? External kuvvet? Yoktur değil mi? Dolayısıyla kuvvetin toplamı ne olmak zorunda? Zero. There is no total force on the cross section. However, if you take a portion of this, obviously you would end up with a non-zero force. Don't forget this. Okay. Again, let's follow the procedure. Bunu tekrar yazacağım. İyice otursun diye. Okay. First, find the centroid. İleride çünkü sentroidi bulacağım problem de olacak. Find the centroid. It is known. It is given, let us say. Okay, in this problem. Second, find principal centroidal axis. Find the principal centroidal axis. Due to symmetry, Y and Z axis are principal centroidal axis, so no problem with that. Otherwise, you have to find by the equations that I mentioned, principal centroidal axis. And then the last thing is the moment, find the components of the moment, find the components of the moment, although not clear from the problem, on the principal centroidal axis. On the principal, yukarıdakilerin aynısını yazıyorum esasında. On the principal centroidal axis, M is on the z-axis. M is on the z-axis. Okay. Anyway, so everything's okay for this problem. There is symmetry, you know, centroid, everything. Now I'm going to throw another figure to make the problem further clear. So now here is the cross-section that we are referring to, right? And on this cross-section, the centroid of the problem is already given. This one says C. And we have given axis. We don't need to locate any axis in the previous problem. So Y and Z. The problem says that there is a moment. Look at the statement of the problem. There is a moment about horizontal axis, but it's not, direction is not given. So I don't like such definitions. I am just assigning a moment to the problem. Yes, it is horizontal with this direction. So this is MZ. Now the problem says that find the force in the flange. So it says find the force in this area. Which area? This area. Okay. So what I'm going to do is this. First, I am going to take an infinitesimal element here, this one, which is dA. Clear? Okay. Now, on the area dA, on the, let me write the, let me write shortly. On dA, I have the following force. I have an infinitesimal force, and this force obviously is equal to the normal stress on that force due to bending, sigma x. It should be perpendicular to YZ axis times dA. Okay. However, I know that for this cross section, sigma x is equal to minus mz times y. Now remember our equation that we already obtained, times dA. Clear? Okay, this is the force acting on that infinitesimal area. I am looking for the total force. What is total force? Total force is F. Okay, so F is equal to integral of this area on AF. So say that, look, this cross-hatch area, I mean, this area, let us designate it as a flange. The flange area, okay, a part of the cross-section, not all. Anyway, on the AF, I have minus mz y over iz times dA. Well, it's equal to minus mz, is a constant, over iz times y dA. Now, what is y dA? I asked this question to you in the previous problem. It is the first moment of area. So We know that first moment of area is this. It is minus mz over iz. It is the y bar of the cross-sectional area times corresponding area. Why? Remember statics. We determined, for example, y bar as integrating it on the integrating dA and dividing y total area. Remember statics. This is the way how we determine the centroids. So if this is 0, it means that you are referring to centroid. If it is non-zero, it gives you YF. Okay, let's turn back to this problem again. This integral y dA is also equal to AF times, AF times this distance. Which distance? The distance of the centroid. Okay, here is the centroid of the cross-section. Now we know that this distance is YF. Okay, they are the same because this is the centroid of the cross-section. Clear? Burada anlaşılmayan bir şey var mı arkadaşlar buraya kadar? So now either evaluate y dA for AF or multiply integral of y dF or multiply it with the centroid of area times corresponding cross-section. Now, the remaining is finding moment of inertia, YF, AF, etc. Any question of this point? Bundan sonrası kolay çünkü. Peki. Şimdi, now, to solve this problem, okay, we need to calculate moment of inertia. And for this purpose, I'm going to use two areas. Now, say that this is the first area and this is the second area. And then this is the centroid of the first area, C1, where this distance is dy1, that's equal to 36 millimeters. You can calculate it. And say that this is the centroid of the second area, C2. And this distance from here to here is, again, dy2, that's equal to 36 millimeters. Is this clear? I am using to determine the moment of inertia two different rectangles. One is the cross-hatch rectangle and the other one is the vertical area. C1 is the centroid of the first area, this one. C2 is the centroid of the other area. C1 and C coincides with each other. Okay. Okay. Then, now, statikten hatırlayın arkadaşlar. Bakın, takip edin hatırlamak için. Moment of inertia of the first area. Now, I am looking for IZ1, the first area. What is the equation? 1 over 2f d1 h1 cube plus a1 dy1 square. That is 1 over 12. d1 is the width of the area, or is the dimension of the area parallel to the z-axis. Parallel to the z-axis. If you look at the figure, it is 216 millimeters. So 216 millimeters. H is the height of that area, which is 36 millimeters to get the figure. So times 36 millimeters to power 3 plus A1, which is 216 millimeters times 36 millimeters, as clear from the figure, although I don't have the dimensions, the above figure has. Now I am going to multiply this distance, this area, with the distance between the parallel axis passing through the centroids of these two, which is dy1. That is, again, from the figure is 36 millimeters. Okay. So if you calculate this, you will see that moment of inertia of the first area about z-axis is 10.9175 times 10 to the power 6 millimeters to power 4. Anlaşıldı değil mi arkadaşlar? Şimdi IZ2. Peki. Asiye Nur Özcan. Şeyi hatırlıyor musun? Yazdıklarım üzerinden giderek istersen söyle. İkinci alan için bunları bana söyleyebilir misin? Yani 1 over 2f B1, sorry. Ben yazayım istersen, sen nümerik değerlerini söyle. B2H2 cube plus A2 dy2 cube. So, look at this. Second area, what is B2?
108.
Now look, hepiniz hatırlayın arkadaşlar lütfen. Now, if this is the z-axis and if we are writing iz, B is the distance parallel to the z-axis. H is the distance perpendicular to the z-axis. One is parallel, the other perpendicular. In that sense, since this is the second area, what is B?
72.
72, yes. It is 72. Biraz önce B kaçtı? 216 değil mi? Burada 72. So 1/12 times 72 millimeters. Peki H yükseklikte geri dönüyorum. What is H?
108'den şeyi çıkarmalıyız değil mi hocam?
Yes, 108. So it is 108 millimeters to power 3, right? Okay. Plus the area is clear. 72 millimeters times 108 millimeters. Now I'm going to multiply it with the distance between these centroids. If you look at my figure, what is that distance?
36.
6, yes.
Yes.
So this distance is the distance between two parallel axes. One is passing from the second area centroid. The other one is the overall centroid. So it is 36 millimeters. So again, 36 millimeters. Although it is not important in this problem, this is a minus quantity because in the product of inertia it is important. Here not. But if we are calculating product of inertia, these signs are important. So don't forget to put the signs to here just to get used to. Okay. Then this is equal to 17.636 times 10 to the power 6 millimeters to power 4. Okay. So now here is the result. Of course, I am looking for the moment of inertia for the whole cross section, which means that just add these two. As a result, bunu biraz detaylı yazdım. IZ, bunları bilmenizi bekliyoruz arkadaşlar, unutmayın. Is equal, total moment of inertia is this a composite approach, sum of these two, and that's equal to 28.5535 times 10 to the power 6. So this is the total moment of inertia of the cross section. Now, look at our equation. We need what? We need YF and AF. YF is clear. YF is 36 millimeters. AF is the area of the flange. Now, the flange, the upper portion is equal to the same 260 millimeters times 36 millimeters, and the area of the cross H1 or the flange is 7,776 millimeters squared. And YF, as very clear, is the centroidal distance is 36 millimeters. Bütün değerler aynı çıkıyor aşağı yukarı. Then the force is equal to minus, now I'm referring to this figure, look here, this figure, MZ, IZ, YF, IF. So we found MZ is given as 6 million newtons millimeter. We found IZ 28.5535 10 to the power 6, okay. Then we know YF, which is 36 millimeters. We know AF, which is 7,776 millimeters squared. Now from here, you end up with the following value. Force is equal to minus 58,820 newtons. Is this clear? Peki. Şimdi Selin Korkem. Duyuyorsun değil mi beni Selin?
Evet hocam.
Selin, şöyle bir force bulduk. We found this force. And now we know that this force is acting on this cross H area. Is this clear?
Yes.
Yes. But we know that there is no external force on the cross section. So If I ask you, what is the force on this area? What do you tell me?
I don't know hocam.
Düşünerek cevap verirsen bulacaksın bak. Mavi alanda, şu alanda bulduğumuz kuvvet aşağıda, tamam? Ve eksi. Bir şey daha biliyoruz. Bu cross section'da toplam kuvvetli olmak zorunda. Sıfır, değil mi? Çünkü eksternal bir kuvvet uygulamıyoruz. O halde alttaki kısımdaki kuvvet ne olacak? Buna bakarsan sıfır olması için.
Tersi
Tersi
tarafta.
olacak. Evet, aynen dediğin gibi tersi olacak. Çünkü burada sadece moment var arkadaşlar. Kuvvet falan yok. As a result, if there is a compressive force in the portion that we have calculated, there must be a same amount of compression tensile force at the bottom. So when we add them, it should add to zero. Is this clear? Shortly, in pure bending, on any cross section, be careful in pure bending, on any cross section, there is no net force. Zero. But if we just take a portion of it, of course there is support because upper portion is in compression about the neutral axis or vice versa. Lower portion is in tension. So when you add them, the result is zero. But if you just consider a portion of that as we did here, there is a non-zero force distribution. Is this clear? Okay. Tamam mı arkadaşlar? Dolayısıyla bu kuvvet sadece belli bir kısmını hesapladığımız için var. Toplam kuvvet sıfır. Peki. Sanıyorum anlaşıldı. Pek bir zamanımız kalmadı. 3 dakika var.
Hocam bitirmeden önce soruyla alakalı bir şey sorabilir miyim?
Esasında şöyle yapayım. 3 dakikamız var değil mi? Hiçbir probleme başlamayın. Çünkü şeklini kopya edeceğim kalacak. Onun yerine bu sorunuza cevap vereyim. Evet, kim sordu? Yes, what's the question?
Ben sordum. Hocam birazcık daha yukarı çıkabilir miyim? Burada YF ve AF olarak çıkardık ya integralden. O kısmı
Evet.
bir daha bir tekrar edebilir miyim?
Sorunu anlayamadım. Tekrar söyler misin?
Hocam F eşittir eksi MZY dA bölü Ix yaptık ya. O integralin sonucunda YF AF'in nasıl çıktığını pek anlamadım. Onu tekrar bir anlatabilir misin?
Şöyle. Bu dersle alakalı değil yalnız o. O şu. Statikte hatırlarsan statik kitabına bakmanı tavsiye edeceğim. Sentroidi nasıl bulursun? Bir alanın sentroidini, x barını. Mesela şöyle bir alanım var. Bu da dA olsun. Şu da koordinatların olsun. X ve Y. Şimdi ne yapalım? X barı bulmaya çalışıyoruz. Şöyle yaparız değil mi? X barlı çarpı A'nın toplam alanın yarattığı moment bizim dA çarpı X'in yarattığı momente eşit olmak zorunda değil mi? Doğru mu?
Evet.
Yani buna esasında biz tilde demiştik hatırlarsan statikte. Şu alanın yarattığı moment integre edildiğinde bütün alanın yarattığı momente eşit olmak zorunda. Doğru mu?
Evet.
O zaman bu bizim sentroidi verir dedik şurada. Dolayısıyla x bar eşittir dA times x integral over a'dir. Bu formülü kullandık. Tamam.
Tamam hocam. Teşekkürler.
Shortly, first moment of area, of course, using the proper coordinate systems, gives you the location of the centroid. And that equation is integral of dA times x over the area over area. Clear? So please look at the static book for this, but we use this equation for centroid.
Tamam, teşekkürler hocam.
Oraya bakarsan hemen hatırlayacaksın zaten. Başka soru var mı arkadaşlar? Evet. Burada mı? Bu sayfada mı? Evet. Tabii. Sentroidi bulman gerekecekti önce. Yani o biraz daha uzun olacaktı ama bulacaktın. Yani diyelim ki taralı alanımız, mavi alanımız, hani senin dediğin gibi şöyle bir alana bakıyor olsaydık, o zaman sentroidi burada ben tabii direkt koydum. Çünkü belli rectangle biliyorum. Ama şurada bir yerde başka bir sentroidi bizim statikten bildiğimiz yöntemler bulmamız gerekecekti. Geri kalan değişen bir şey yok esasında. Ama taralı alan evet yani böyle gidecek. Anlatabildim mi? Peki başka soru var mı arkadaşlar?